Okay, our second talk is by André Carlon. He is a postdoc here at KAUST, and he will be talking about Bayesian quasi-Newton method for stochastic optimization. The stage is yours.
Thank you, Aku. So as Aku said, I'll be talking about our approach for Bayesian quasi-Newton method for stochastic optimization. This is a joint work with my collaborators, Luis Spaff and Raul Temponi. So first, I'll talk about the problem that we are trying to solve here, try to motivate the development of this class of methods, quasi-Newton methods for stochastic optimization. Then we'll talk about the problems on devising such kind of methods and proceed with the methods itself. How did we formulate them? How do we solve the sub-problem that we have to solve to get our approximations? And finally, show some numerical examples. So the problem that we're trying to solve here is an optimization problem. Here we have function f, and defined as uppercase f, and we have xi as our design variables, our optimization variables. And what we want is to find some xi star that minimizes f. So this is a general deterministic optimization problem that we have in one, and we are specifically interested in this case where f is some expectation, as here, where we have some f as some expectation of some lowercase f function that is also a function of some random vector theta. We assume that we can sample from the distribution of theta, and we can also evaluate derivatives of f, and we hope to find xi star that minimizes this expectation. So let's lay some assumptions here on f. So we assume that f is Lipschitz smooth with some constant L, and we assume also that f is μ-convex, so we have strong convexity. Now, if also f is twice differentiable, we have lower and upper bounds on the eigenvalues of the Hessian of f, and the ratio between the upper bound and the lower bound is called the condition number of the problem, which is a very important quantity here for us, because this number could be quite large and might bring trouble to our convergence. So we discussed two simple methods for deterministic optimization, which are the gradient descent, the canonical first order method, where we take steps in the opposite direction of the gradient. And this method for this setting is known to converge linearly, or the optimality gap here converges linearly, and we have a number of iterations that is linear on kappa, the number that I just shown you. So on the other hand, we have the Newton method, which is a second order method where we precondition the gradient by the inverse of the Hessian. And in this setting, we, given that we have some stability conditions satisfied, we have quadratic convergence. And in this case, we get rid of any dependency on kappa. So as I said before, large kappa here can be a big problem. So we want to get in this direction of something closer to second order methods. Now, one way that this is done in deterministic optimization is on this class that are named quasi-Newton methods, where instead of computing this direction D, a search direction D that is the solution of this linear system that could be expensive, we use just the gradient information on the history of the path of optimization to devise some preconditioning matrix that we hope to approximate the Hessian. For example, here I am showing you the formulation of the DFP, the Vidon-Fletcher-Powell method. And this method, every iteration you start with some approximation of the Hessian, here denoted as bk minus 1. And you find the next Hessian approximation by minimizing this proximality term here, this norm, which is a weighted Frobenius norm centered at the previous Hessian approximation, while satisfying these constraints of symmetry, and very importantly, the second equation. The second equation here is what would make this matrix closer to the Hessian, because here S, notice that is the difference between the iterates, and Y is the difference between the gradients evaluated at these iterates. And to derive the DFP here, we also need W, this weighting matrix, to satisfy this condition. Now, to make this a bit more clear intuitively, I made this cartoon showing here this subproblem of finding the Hessian. So this is a space of matrices, symmetric matrices. And here I have the objective function, the contour of the objective function centered at the previous iterate. And in blue, I am representing the affine space of matrices satisfying the second equations. So what is done is one minimizes within this subspace this proximality term, and then you find a good Hessian approximation, hopefully good, right? Now, okay, this works in deterministic optimization. Now let's see what we can do in stochastic optimization. Well, the difference from deterministic optimization and stochastic optimization is the kind of data we have here. We cannot assume that we can observe the true gradient, but instead we have some noisy gradient observation denoted here. So what epsilon here denotes? It's like, for example, it could be a Monte Carlo estimate of the true gradient. It could be some variation given by some control-variance method, like mice, which was devised here in our group, or SVRG and SARA, quite standard methods. And in any case, we have to, given that we have some control on the statistical error, all of these methods, they guarantee that you have this condition satisfied. Then you should recover the order of convergence on the deterministic gradient descent method, and then you have recovered this linear dependency on kappa. So again, we have the same situation as in deterministic optimization. What can we do? So can we devise line search-free quasi-Newton method for stochastic optimization? So can we use this information that we have available to derive some approximation, some matrix here that to precondition our gradient estimate in order to make SGD faster? Especially, we want to avoid this low convergence problem that we have when we have large condition numbers. Well, to do so, we need to answer a few questions. The first one is actually how to really learn about the Hessian from these noisy gradient observations. I mean, we cannot just fit the secant equations here, because the secant equations, we don't have the true gradients, and we have noise on the information that we have, so we have to do something else. Anyone that tried using BFGS on noisy gradient found out that it diverges badly and usually goes anywhere other than the optimum. Now, the second problem that we have here is how to avoid amplifying the noise that we have in the gradient, because it's possible we have this gradient estimate with some noise. Once we precondition by this matrix, it might have some really large eigenvalues in some directions, and then we might have this problem of noise amplification in some directions. And finally, is it even enough to have some good Hessian approximation acting on noisy gradients to have convergence? Does this even work? I mean, so let's see. Now I'll talk about our method, our approach. I hope you are convinced that this is important enough. So, okay, so let's lay down some notation here. So in deterministic quasi-Newton methods, as I just said, we have access to this yk here, which is the difference of the gradients evaluated at subsequent iterates. Now, this is what is used in deterministic quasi-Newton methods. However, in our case, we do not have access to y. Instead, we have access to evaluations of lowercase f here, and we can evaluate this for thetas that we sample. But still, we can build this quantity here, y hat, which is still a function of theta. And then what can be done is to build some Monte Carlo estimator here of y that we denote as y bar. And it's important here also to say that we assume that we have all this data from optimization. We are not evaluating anything extra just to compute the hashing. These are the gradients that we use in optimization. And okay, now how do we use this information to build a hashing approximation? Well, we use Bayesian inference. In fact, to formulate this problem here, we gather all these y bars in a set y, and we gather all these s's in a big set S. And then we use Bayesian inference to build a posterior distribution of matrices B given S and Y by constructing a likelihood distribution of observing the curvature pairs, as we call them, given B, and the prior distribution of B, where we encode the knowledge that we have about this matrix a priori. So once we have some posterior distribution for our matrix, we set our quasi-Newton update as the maximum a posteriori of this distribution. So here I'm laying down the problem that we want to solve. We want to find B that minimizes this negative log posterior. And here I sneak some conditions. We want to have some lower and upper bounds on the Hessian approximation that we have. And of course, we want symmetry. So first, let's talk about the prior distribution that we are assuming for our Hessian. You can see that what we opted here is to have a negative log prior that is very close, basically identical to the one that it's used in the deterministic Quasynical methods, which is this weighted Frobenius norm squared. The idea is the same. We want the Hessian that we get to be as close as possible to the current Hessian update. Of course, this also gives us a good regularity on the problem that we're solving. And also, we have some eigenvalues constraints. So we use logarithm pairs to keep the eigenvalues of B within U hat and L hat. Right, so say we are in the space of B's, and as we get closer and closer to having some lower eigenvalue mu hat, this determinant goes to 0, and this log barrier explodes to infinity. So the idea here is to encode on the prior this knowledge that the eigenvalues should be between U hat and L hat. And this is very important. I will talk soon about why keeping these eigenvalues controlled is so important. Okay, now let's talk about the likelihood. If you see, this quantity here is the residue, some form of misfit of the secant equations that we have, given that we do not observe y, but we have this Monte Carlo estimate. And this is, in my opinion, the central point of our work, because here is how we incorporate the knowledge on the Hessian of the curvature pairs, the noise. So what we do is not a big crime. We assume that the error on this misfit is Gaussian distributed, because this comes from some Monte Carlo estimate, of course. And then here we have the sample size, right? And we assume also that this covariance matrix can be computed. Of course, and then for one curvature pair Sy, we defined this negative log term, likelihood term, as denoted here, where P is a precision matrix, the inverse of this covariance matrix here. Now, as I said, we have several curvature pairs from several iterations that we are storing in memory. And then we defined our negative log likelihood here for all data points as the sum of these terms here. Okay. So we have the prior, we have the likelihood. Oh, yeah. Let me mention this is basically a normalizing term to avoid that the likelihood dominates the whole thing. A bit arbitrary. So here is the negative log posterior as we built, defined over this space of symmetric matrices, where we also include here these constants, rho and beta, strictly positive, which we use to weight the two terms of the prior, right? This proximality term and the log barriers. Now, as I said before, we will pick this B hat here, our Hessian estimate, to be used as a preconditioner as the one that maximizes this function. Minimizes this function, sorry. So in the same spirit of the other cartoon that I've shown you before, here I am showing you the prior, the likelihood, and the posterior. So the prior is basically the same as for the deterministic case, except that now we have these constraints as these shaded regions here, where we cannot enter. Now we see here in the likelihood this affine space where this secant equation is satisfied, but of course we're not fitting it. Instead we have the likelihood as the probability of getting close to this is larger, right? And this probability decreases as you get farther and farther away, depending on the precision that you have on this, the knowledge that you have on this Y bar estimate here. So combining the prior and the likelihood, we have something like this posterior, where we will get a minimizer of the negative log posterior here as denoted on this big X here. Of course, this posterior itself depends on the parameter rho that was weighting the proximality term. The larger rho is, the closer this will be to the previous one. So we can say that we are more conservative, the larger rho is. And if we let rho goes to 0, we should get the deterministic BFGS update here. So we have this one parameter that really weights in how much confident we can be with the information that we have. Now, once I define the problem, I define what I want, but how do I find it? How do I solve this problem of finding this matrix? So here we have some nice structure about our optimization problem here. These two terms are convex, and this term is strongly convex with parameter rho. So we can exploit this to try to devise some good numerical method to solve this subproblem. Specifically, what we do is we use the Newton CG method, which is Newton with conjugate gradient, so that the conjugate gradient is used to find the Newton direction. So we don't have to assemble, say, the second derivative fourth order tensor of this negative log posterior. And then once we have the Newton direction, we use backtrack Armijo to do the line search and find the update. Now we have also to deal with this beta parameter here. Beta, we would ideally want beta to be as small as possible, but this also causes this subproblem of this subproblem here to be ill-conditioned if we let it be too small. So we use this inter-point path following approach to start with some large beta, and then we keep decreasing and solving Newton CG methods until we get a small enough beta that does not bias so much the solution. So here I even laid some pseudocode to illustrate what we're doing, to show that it's not so complicated. Here in the loops 3 to 11, what we're doing is the path following approach. We keep the decreasing beta by some factor gamma here. And then here on this loop, what we're doing is the Newton CG approach, where we try to find some direction D. This is a matrix, right? where that would be the Newton direction. We have to use conjugate gradient to find this. Now this can be computed directly. We have a closed form for this directional derivative. And solving this, we have the direction, and then we have to use backtrack-Hermitian to find a good step here to update the hashing. We do this until this condition is satisfied. We reach some tolerance and repeat until beta is small enough and tau is small enough. So, okay. I've shown you some Bayesian framework for learning about the hashing. I've shown you how a method that we propose to solve this subproblem. Now let's look at these questions that I laid before. Okay. How do we build hashing approximation from noisy gradient observations? As I said, we build this probability distribution, and we use Bayesian inference to learn about the hashing and use the maximizer of the posterior as a hashing approximation. So how do we avoid amplifying noise? And here I get to the point of controlling the smallest eigenvalues of B hat here. Because given that we control the smallest eigenvalues of B hat, we also implicitly control this operator norm here of the inverse, which will be 1 over mu hat squared, right? So we cannot, by forcing mu hat to be somewhat large, we avoid this noise amplification. And finally, how do we guarantee that how do we check actually if this approach works? Yeah, we have to look at the numerical examples and where we will compare the situation where we precondition SGD with our hashing inverse, and we control and then not control the error to see the difference. Okay, so let's look at some numerical examples. We're going quite fast. So first example, just to illustrate how it works, is a simple quadratic function. To be minimized, we will compare SGD, classical stochastic gradient descent, and SGD with mice, which is the method that we derived for variance control. And in both cases, we will compare with and without our preconditioner and see if we can get some improvement. Also for SGD, we compare two situations where we keep the step size fixed, and another one where we keep decreasing it. So here are the results. Here I am showing you the optimality gap per iteration. All methods were run for the same amount of gradient evaluations. And what we have here is in blue SGD. You can see that it takes 10 to the 7 iterations to converge. And now for the cases where we are preconditioning by our Bayesian quasi-Newton method, we denote here this Bay in the name. In red, we have the case where we precondition SGD with our Bayesian matrix, and we can see that the updates are denoted here by this black square. Oh. And when we do the update, we see that we do a big jump here of roughly 4 orders of magnitude to the optimum, which is good and somewhat expected given the problem is quadratic. 1 Newton step should get you to the optimum, right? But still, we have this oscillation problem because in this case, we are not controlling error on the noise of the gradient. Another situation, even worse, is when we keep the step size fixed. In case you don't know, in SGD, we decrease the step size to control the error, right? Here in purple, what I'm showing you is the situation where instead of decreasing the step size, I keep it fixed. And it doesn't help much. We have a larger amplitude here of oscillations. Here you even see some pattern of decrease somewhat here. Here is even worse. Now, when we use mice, SGD mice, to control the relative error of the gradient estimates, we have a nicer convergence. And specifically, when we use our preconditioner, we get even nicer convergence, going much further, even with just 3 Hessian updates. So this is a point maybe I forgot to mention before. We do not plan on using this every iteration, because of course we are solving this subproblem. We are solving this Newton CG with interior point path following method. So what we propose here is that after a certain number of iterations, a few times during optimization, you should do this preconditioner matrix update, and hopefully it will progressively improve the convergence of the method as we see here. Now, this is a 10-dimensional problem. We have a condition number of 1,000. If we do the same thing, but we increase the condition number to 10 to the 6, it's clear that SGD and even SGD mice just don't converge at all. And I mean, they do converge, but the rate here is really bad. It's not even visible. It looks like it's flat. So this is the kind of situation of large kappa where we hope that preconditioning by our matrix approximation of the Hessian should improve the convergence. And indeed, we see that it works. It took a few updates to actually learn some good representation that brings us some improvement, but it did happen. And same thing, the other methods are still weakling when we don't control the relative statistical error. Okay, so now let's look at a more realistic problem. Here we have L2 regularized logistic regression, where we are trying to fit data, right? We have a model. The model has some parameters, and we have features, we have labels, and we are trying to make the model predict the labels of data, given features. So here we got this L2 regularization term as 10 to the minus 5. And we test 2 data sets, cod RNA and mushrooms, quite standard data sets. So first data set has a small number of features. There's a small number of optimization variables, just 8, but has a really large condition number. And the second case has a much larger number of dimensions. So interesting in this sense, but somewhat smaller condition number, even though still quite large. I'll notice that here we will have 112 dimensional problem, meaning that the Hessian that we're trying to approximate is 112 by 112. So the dimensionality of the number of components of Hessian grows quite fast. It grows quadratically, of course, with number of design variables, of optimization variables. So okay. Now here what I'm showing is the optimality gap for the cod RNA data set with a really large condition number. We are comparing SGD, SVRG, SGD with mice also, and SARA on solving this problem, each with its color, and then the counterparts where we precondition with our Hessian approximation inverse is dashed lines of the same color. And again, we showed this Hessian updates as this black square. So here we see that we did only 4 updates on this optimization procedure for each method. Now, what we observe again is that all methods where we do not precondition by our matrix approximation, they just get kind of stuck, converging very slowly. Whereas once we start preconditioning by our matrix approximation of the Hessian inverse, we start to have to see a much better convergence rate, regardless of the really large condition number of the problem. Now, SGD mice seem to profit more from this preconditioning than the other controlled methods, SVRG and SARA. Also, I think it's important to say that these methods, both MICE, SVRG, and also SARA, they rely on computing gradient differences to compute their variance reduction approach. So they already have this curvature pair information available. We don't have to do much. We don't have to pay more to get data. Data is available. We have to pay to find this matrix approximation. Okay, but here I'm showing you convergence, but I'm not showing you runtime. How much time do we spend on each of these updates, right? Maybe it's much more than the whole optimization itself. So let's see here. I'm showing you 4 plots. Each one of these is for one of the 4 Hessian updates that we had. And these are actually conversions of the Newton CG method used to find the preconditioning matrices. So in each color, I have a different path following step, meaning that I start with some large beta. When I reach this threshold, I decrease beta and I repeat until I get to the desired tolerance. So each dot here is a Newton step, right? And these black numbers on top of each Newton step is the number of conjugate gradient iterations that were needed to find the Newton direction, which is actually it's our cost. It's where is the big bulk of the cost of this method. And we can see here that for this problem, the number of conjugate gradient steps and the number of Newton steps were very reasonable. And very importantly here, we have the time spent on each one of these workstation that didn't exceed 2 seconds for this problem. So to observing the advantage that we have here, I think this is a good deal, especially because if you don't use it, these other methods don't seem to go anywhere. And finally, let's look at the other data set where we had a much larger dimensionality, same algorithms. And again, we observed that, say here, SGD mice is doing well, converging even, but still by using our preconditioner, we are able to get an edge here of almost 2 orders of magnitude, almost. And also, it's an even larger advantage if we look at SARA and SVRG. Okay. And again, as I said, this problem is we have 112 optimization parameters. So the cost of solving this problem is much more significant. And in this case, we took almost up to 25 seconds each time we were solving this problem. But still, something interesting is that neither the number of Newton steps nor the number of conjugate gradient iterations were too large, actually not exceeding 18, right? Which is quite good. And okay, so let me conclude here. So what we did is presented a maximum a posteriori Bayesian approximation to extract second-order information from noisy gradient estimates, and thus develop a quasi-Newton method or a class of quasi-Newton methods, to be honest, for stochastic optimization. So we modeled the log prior using a weighted Frobenius norm and proximality term and the log barriers to control the eigenvalues, thus control stability and noise amplification. Also, as I said, we control the eigenvalues bounds and control the noise amplification. And we use the likelihood to learn from the gradient, even though we have just noisy information. And given that we have this nice structure of strong convexity of our log posterior, negative log posterior, then we can use Newton's G to find the maximizer of the posterior. And finally, I think it's good to point out that this inverse Hessian approximation can be used with basically any first order optimization method in stochastic optimization, and is specifically interesting on these cases where these gradient differences are already computed, like in mice, SVRG, and SARA. So, okay, this is the first of what I hope to be a series of works where we develop these quasi-Newton methods for stochastic optimization. And we already have ongoing work on low rank approximations of the matrix to try to run away from this OD cubed cost that we have so far, try to get something better. We already have some promising results. Also, something that we didn't touch here, which is how to pick which curvature pairs Y and S we keep, which ones we discard, because we have finite memory, of course. And when should we do the Hessian update? Here we set a fixed number of iterations. Maybe we can do something more refined, do some tests to check if the approximation we have so far is good, to decide when to do the update. And finally, we are working also already on developing line search methods for stochastic optimization. There are some works published already on this, but it's still kind of an open problem. There's still a lot to be done. And a line search would, I believe, assist fast convergence and even give guarantees of convergence even on non-convex situations. If you're interested, you can install our implementation in Python using pip. It's available on PyPy. And the source code is also available on GitHub. And if you do test and you run and you find bugs, you can email me, try to address things. So here are the works mentioned. This is our paper, is already on arXiv and it's submitted. This is the mice paper and the other two methods of SVRG and SARA. So that was it. Thank you very much.
Okay, thank you, Carlon, for a very nice talk. Any questions?
Andres, thank you very much. Can you please again repeat what could be here useful for general topic and what is your particular case? So somehow, what is common theory and what is numerics somehow?
What is common what?
Common theory.
Common theory?
Yeah.
What is common theory? You mean in deterministic optimization?
Stochastic optimization, yes.
Well,
so what are general results and what is?
What are general? This we derived. We came up with this formulation, right? Mm-hmm. We came up with the idea of building this likelihood, where we have this form to acquire the information about the Hessian. There is one work that uses a Bayesian modeling for the same problem, but the formulation is very different using Gaussian processes. There is another work that does not use Bayesian, uses more like a frequent twist approach, but also requires solving a subproblem. And Also, the log barriers were our idea. I mean, basically, what we are using from the deterministic quasi-Newton methods is the prior, which is identical here to what is used on deterministic quasi-Newton methods. So I think this will be common theory. And also, the idea of using Newton CG was our idea to exploit this strong convexity and this structure. Yeah. It was built to be strongly convex. If we don't have this proximality term here, then unless you have enough curvature pairs and some other conditions, then you don't have ionic solution.
I'm
Right.
sorry, this is key equation of the whole work.
Yeah,
yes?
yeah.
And to optimize it, you need gradient, you need Hessian, yes?
Yeah. I mean, we do derive this in closed form. Yeah, what we do here is you see this term here, the directional derivatives
Which
of the
line?
direction.
Sorry, it's no.
Oh yeah, I'm pointing to my screen. This term here, you see. So we do not assemble this Hessian. This would be crazy because this will be a fourth-order tensor of dimension of the problem, right? So we can compute directly the action of this fourth-order tensor over this matrix, which is the derivative of the negative log likelihood with respect to B. And we can derive this because I even added here because I thought maybe someone would ask. So this is what we compute, right? This is the gradient. We have everything here. Yeah, I forgot to mention that in our work we just use the weight matrix as the identity, but we kept it for generality because if you don't use the identity, you get different quasi-Newton methods. But still, this is the formula for the gradient. We have everything here. We can just compute. And for this directional derivative of the gradient on any direction of any matrix, symmetric matrix V, we have this.
I'm sorry, and small intermediate question. So you reconstruct here matrix B, yes? B capital.
Oh, B is an argument.
It's not matrix, yeah?
It's a matrix.
Matrix, yeah.
Yeah. It's a matrix. It's a symmetric matrix, necessarily.
And you need to find it, yes?
Yeah, we are computing the gradient. So say we are starting at some point. We plug in this matrix here. We compute the gradient, which will also be a matrix, right? And then we.
So you use maximum likelihood estimation, yes?
No. We're maximizing the posterior. Yeah. So here you see we compute this. This is the formula I just shown you, right? This here. Then we also compute this other term here for some candidate direction D. And then we use the conjugate gradient approach to find D, right? So D appears here again. You see D, here D is V, but it's because I call D the Newton direction, but this is for any arbitrary V. So I'm trying to find V such that this quantity equals the negative of this quantity. And we use the conjugate gradient to find the Newton direction here, to find what is the matrix that if I plug in here, we'll solve this Newton equation.
So, and output of this optimization procedure is matrix.
Yeah.
And do you fix a class where this matrix live? Or it could be general matrix.
It should be symmetric. We impose this, and actually the formulation forces it to be symmetric. And also, yes, you also if we have this necessarily from the way that we formulated the problem, this matrix it has bounded eigenvalues that are strictly positive. Yeah.
Okay, thank you.
Yeah.
Thank you very much.
You see, that's what we return here, like
Yeah. So
Arvid.
okay, so this is the questions. This one?
Oh yeah.
Ah, okay. I'll just read it. Great talk. Do you impose any conditions on the objective function in terms of the stochastic variable? And how does this dependence affect the different methods? Do the Hessian updates yield greater improvements compared to SGD if the function is less regular in theta?
Sorry, what was the first question?
Can we unmute him somehow?
Hi, can you hear me?
Oh, yes.
Yeah, thanks. You showed conditions on the objective function in Xi at the beginning.
You mean here, like Lipschitz continuity?
Yeah,
yes. And smoothness.
So I assume they have to hold for any theta.
No, this just have to hold for the expected value for the objective function f. It should not hold, say, almost surely for every f for every.
Okay, so you don't need any conditions in theta.
Depending on theta, no.
Okay,
We just have the condition on the expected value of f for any theta.
But what I was wondering, if your function is, say, less regular in theta, does your method work better compared to SGD, or?
No, it's a matter of analysis. Maybe if you have stronger assumptions on your objective function, you can derive better analysis. But here we're not getting so deep into the analysis. Our goal on laying down this assumption is basically to motivate why we have this condition number, right? In fact, I mean, we are deriving the whole method and we are using these assumptions, but there's nothing forcing you to actually have these assumptions on the method itself. You might have a function. Okay, smoothness is important, right? Twice differentiability. But maybe if you have a function that is non-convex, you can still use the method because we are forcing the constraints on the eigenvalues, right? As it's done in deterministic quasi-Newton very often. Yeah. Even if your real Hessian is not positive definite, you can still force your approximation to be positive definite, and that's what is done in the deterministic quasi-Newton methods for non-convex functions. And we can still do this.
Okay. And another question I had is have you considered using SGD first and then only doing the Hessian updates once you don't see any improvements for a certain number of steps?
Yeah, that's a good point. I mean, what we do in practice, if you see our convergence plots here, we start with SGD, but then we have this fixed steps at each iteration. We're not doing any sort of adaptivity, as you mentioned, but it's on our plans for future work on doing something like that. Yeah.
Okay.
It's still complicated because if you don't have a good quality gradient information, it's hard to decide that you are not converging. You see what I mean? It makes sense if you're using mice, for example, because on mice we are progressively sampling more to keep the statistical error in check. So yeah, we can assume that we have a good gradient estimate. So we might say, okay, we're not improving any further. We are walking too slowly. So maybe we can do an update and improve this convergence, right? So I think that's your idea, right?
Yeah, maybe some heuristic if you have a certain goal and a tolerance goal and you have a budget for your whole computation time. Maybe after some time, if you're still some percentage away, you could try the updates or something.
Yeah, that's something we have in our head. We just didn't want to investigate this right now, but for sure it's something that we are looking forward.
Okay, thanks.
Thank you, Arvid.
Any more questions? Okay, let's thank our speaker once again. Okay, we will be back here again 2:45.